Hello everybody, welcome to DC Motors Part 3. In this video we're going to talk about how we control the speed of motors. And if you haven't watched Part 1, where we talk about mechanical characteristics, or Part 2, where we talk about electrical characteristics, I highly recommend you go do that. That's going to give you the background you need to understand this video. And yeah, so let's get into it. Alright, so to control motors, we have to be able to modulate the voltage we supply to it, right? So the smaller the voltage is that we supply to a motor, the slower it's going to spin. And the higher it is, the faster it's going to spin. So I guess the question is, for controlling motors, is how do we modulate that voltage? How do we control the voltage we supply to a motor, right? And I guess like you can think back to resistance, right, in Ohm's law. And we learned that resistors can do this, right? Through Ohm's law, right, if we change the resistance we have in a circuit and we put those resistors in parallel, we can control the voltage coming out of wires, right? However, this is not the best way to do it, right? Because the nature of resistors is that it takes a lot of the energy and wastes it in heat, right? And we don't want to waste energy, right? We're running off a battery. We have a limited energy source. We need to make the most of the energy we have, right? So that's why we use something called PWM to control our voltage, right? PWM stands for pulse width modulation. And before I kind of get into the nitty-gritty of it, I have a little live demonstration, so let's go over to that. Sorry about the awkward angle. I'm kind of running off my laptop camera, so it's kind of weird. But here's my simple circuit, right? It has one brush motor. I put this electrical tape just so you guys can see it spin. I have this 9-volt battery, and on my breadboard here, I have a button. Right? You can see this tiny little button right here. And so when I press the button, the motor starts spinning. Okay, super simple. So what pulse width modulation does is, in order to control the voltage and the speed of the motor, it sends rapid pulses through to that motor, right? And I'm gonna look absolutely ridiculous doing this because I cannot even come close to how fast a computer is able to do this. But so okay, say this is it running at 100% power, right? I've just pressed the button down. I'm not letting go. But if I say I want to run a little slower, right? By rapidly pulsating, I'm able to make the motor run slower than that 100% through these pulsations, right? So again, this is 100% power, and this is something less than 100% by pulsating, right? And I'll have some graphs later on that'll help you understand this. But remember, PWM is all about sending rapid pulses to change the voltage over time, right? And kind of slow down that motor to the speed you want it to. Okay. Alrighty, I hope you found that demo useful. Let's go over the PowerPoint slides on PWM. Alright, so as we discussed, PWM stands for pulse width modulation. And so as you saw in the live demo, by providing a series of high frequency pulses, we kind of emulate a lower voltage, right? And the average voltage of all these pulses, right, over time is equal to the target voltage you want to reach. Right? And so this will make sense when I have a graphs coming up in a little bit. But for those who like equations, here we go. So VA sub M is the target voltage, the voltage we're supplying to our motor, right? On time is per pulse, how much time does it spend in the high state, in the 12-volt state, right? And T is our period, which is the amount of time we allocate per pulse, right? So if there's on time, off time is T minus on time, okay? And V sub S is our supply voltage, right? So in the case for FRC, our supply voltage is 12 volts. Okay, so here's some graphs. And so with the first one, right, as you can see with what I labeled in green, the PWM signal is on 50% of the time and off 50% of the time, right? So if we take the average of this over time, right, we find that the voltage we are supplying to our motor, V sub M, is 6 volts. Right? And the one in the bottom right here, as you can see, we spend 25% of the time of our period in our on state and 75% of our period in the off state. So if you plug it into this equation right here, we find that V sub M is 3 volts. Okay. So one thing we need to be careful of when we use PWM as signals is that the signal period cannot be too long. right? And when it is too long, right, what happens is because voltage switching from on to off is not perfect, there's some lag and there's some sag, right? Um, the motor will noticeably speed up and slow down, right? It won't be perfect, a smooth control. It will be very unpredictable, right? And that's why we want a shorter period, because by providing a shorter period, we have a smoother output voltage and thus a smoother control of our motor. And just to show you how the importance of shorter period and how short of a period we're talking about, the Town SRX uses a very high frequency of 15.625 kilohertz switching frequency, right? So it kind of makes the PWM period extremely small so that we have a very smooth control over our motor. All right, and here's some graphs just to help you just visualize this. And again, if you have some tough time reading some of the labels, let me know. But so here we have the top one over here is an example of where our period is too long, and you can see our period marked in green down here. And so because the period is too long, as you can see with the purple line, the voltage kind of sways all over the place and is very unpredictable. However, the graph on the bottom is much better, right? We use, as you can see in the green, we use a much smaller frequency. And because we use a smaller frequency, as seen with the purple line, right, it still deviates, yes, from our target voltage V sub M, but it's not too bad, right? It does deviate a little bit, but it's much smoother. And as you can see, if I were to go even further, make our frequency even smaller, the deviation from the target voltage will become smaller and smaller and smaller and become smoother and smoother, right? So the shorter period we use, the better. All right, so I'm gonna do a quick kind of caveat onto some other PWM applications. One of them is on sensors. So this is a sensor right here, an ultrasonic sensor, and it uses PWM to communicate what it's reading to our computer. And so PWM is often used as a communication protocol. So that's pretty cool. And it's also used in communication for servos, right? So if you haven't used servos before, it's used all the time in FTC. I haven't really seen it used in FRC yet, but that doesn't mean it can't be. And servos are these really cool devices that move to an exact degree measure, right? So through PWM, the computer encodes like go to 90 degrees, right? And the servo will interpret this PWM signal and move to 90 degrees, or it can move to 25 degrees, or it can move to 180 degrees, right? Depending on what PWM signal it receives. So PWM is also used as a communication protocol. All right, here are some examples of some motor controllers we have. And I'm not sure if I said this before, but here we go. PWM, the way we use PWM to control motors only works for brushed DC motors, right? If you remember from our mechanics video, DC motors part 1, right? Brushless motors rely on three-phase electricity. And the thing that supplies this three-phase electricity and kind of modulates the voltage of a brushless DC motor is a speed controller. And the speed controller doesn't use PWM, it uses those three-phase electricity. It might use PWM when it's in its signal processing, but I'm not sure. You probably want to look that up for yourself. All right, so the Falcon FX here and the Smart Max here are two examples of brushless controllers, right? And the Victor SPX here and the Town SX here are examples of brushed motor controllers. And so just to go into them in a little more detail, the Victor SPX, it is kind of the light version of the Town SRX. It doesn't have a lot of the features and capabilities of the Town SRX, but it's a lot cheaper. So if you want to be nice to business, save some money, use a Victor SPX when you can, right? And when you don't need those extra capabilities. The Town SRX is a very, very beautiful, powerful, versatile device. And it even has this little sensor port at the top where you can plug in things like encoders and limit switches, and we'll cover all this in future videos, but just know that plate is there for sensors. Right? And something that the Town FX, the Victor SPX, and the Town SRX have are these LEDs. So Town FX, the LEDs are here. The Victor SPX, the LEDs are these two things right here, and the Town SRX, the LEDs are these two things right here. And the controllers have a blinking pattern in which you can use to kind of understand what's happening with the robot and debug when necessary. And the Victor SPI, the Spark Maxes also have this color LED right here that can help you understand what's happening. Okay, and just another thing to talk about, all of these controllers use the CAN network. So there's these two green and yellow wires that come out of them. You can't see them with these two controllers, the Falcon FX and the Spark Max, but they are there. And so through these green and yellow wires, they're able to connect to the CAN network and communicate to our RoboRio. Right? So talking about RoboRio, what is a RoboRio? Right? So a RoboRio is the central computer for our robot. It's where all the processing happens, and it kind of sends signals to all the other motor controllers and tells it what to do. Right? And so our old motor controllers, they used to plug directly into our PWM port. Right? Those are things like the old Victors and the old Talons, right? But we don't do that anymore because we want to have clean wiring, and we want to make sure there's as few as failure points as possible on a robot. And that's why we use the CAN network. So CAN network makes the wiring much cleaner and much easier. We'll cover this in a future video all about the CAN network, but just know that motor controllers are part of the CAN network. We'll kind of go in more detail in the future. All right. And I talked about those LEDs on the Victor, the Talon, and the Talon FX and the Talon SRX. But here's directly from the documentation, the table that tells you what it means. I'll go over some of the important ones are blinking green, which means you're applying a forward throttle. Blinking red means the motor is going to move backwards, or negative throttle. Often orange, alternating, means that a CAN bus is detected, but the robot is disabled. So this is the nominal state when the robot is disabled, which is good. If it's often orange, it means that everything is connected well. Often red means that the CAN bus is not detected, and if you ever see this, you probably messed up somewhere in the wiring. So, or the CAN bus might not be configured properly, which we'll cover later, but just be aware of that. And the other important one is solid orange. That means a neutral throttle is applied, or zero volts are being applied to the motor, and so it's just sitting there, right? And solid orange compared to often orange. Solid orange is when the robot's enabled. Often orange, it means the robot is disabled. All right. Sorry about the cut. So on to our example problem. Right. Arnav wants to supply a motor with 8 volts of power, but his power supply is 12 volts. His big brain decides to use PWM, right? He doesn't want to waste energy. Right, so what is the signal on time? The switching frequency of the controller Arnav is using is 10 kilohertz. Right, so I'll let you pause. Remember to use that equation we covered a few slides ago. I'll let you pause. All right. So again, the equation we used is V sub m, voltage of the motor being supplied, is our on time divided by our period times our supply voltage. And so if we rearrange the equation, we get the on time is the voltage of the motor times period over the supply voltage. Plug in the values we know. On time is 8 volt times 1 over 10 to the 4th hertz, all over 12 volts, right? Then we get our on time is 6.67 times 10 to the minus 5 seconds. So to run his motor at 8 volts from a supply of 12 volts and a controller of 10 kilohertz, the controller produces 6.7 times to the minus 5 second bursts of 12 volt power in order to get it to 8 volts. It's pretty cool. So that's it for this video. In the next video, we're going to kind of dive deeper into our RoboRio and some different sensors and different communication methods. But that's it for this one, and I hope you guys have a great day.